All right, so far in our systems adventure, we've done distinct eigenvalues, complex eigenvalues, and now the last step to consider are repeated eigenvalues. And in order to do this, let's solve x prime equals ax and draw the phase portrait where A is the matrix 1, 1, minus 1, 3. And so as usual, let's find the eigenvalues. Because remember, if I can do it, so can you. So let's find determinant of A minus lambda I. So that becomes 1 minus lambda, 1 minus 1, 3 minus lambda. Evaluate the determinant. So 1 minus lambda times 3 minus lambda minus 1 times minus 1. And that becomes 3 minus lambda minus 3 lambda plus lambda squared plus 1. And then what we have at the end is lambda squared minus 4 lambda plus 4. Look how cute that is. We have a perfect square, which now completes as lambda minus 2 squared. And you want to set this equal to 0. And what we end up getting is one eigenvalue, lambda equals 2. And since we only have one eigenvalue, this is what's called a repeated eigenvalue. Just like a repeated. What I want to say at the outset, there's no need to panic just yet. Just because we have one eigenvalue doesn't mean that we'll only have one eigenvector. It is certainly possible that we find two eigenvectors and that we can do the same thing as for distinct eigenvalues. So really, all this depends on the eigenvectors, not the eigenvalues. All right, so let's try to find the eigenvector or eigenvectors. So let's do the null space. So null space A minus 2i. Again, remember, you subtract 2 from the diagonals. So 1 minus 2, 1. And then minus 1, 3 minus 2. And then 0, 0. And this gives you minus 1, 1, 0, minus 1, 1, 0, and which is very nice because you can just subtract the first row from the second one, and you end up getting minus 1, 1, 0, and a whole row of zeros. So what this tells you is minus x plus y equals 0. So y equals x, and our eigenvector in this case, v, which is xy, and y is x, so it's really xx. And this is x times 1. So what we've learned is for the eigenvalue 2, we have the corresponding eigenvector 1, 1. And now we can panic because, oh no, we only have one eigenvector. Vector. And the question is, what do we do now? Well, let's think a little bit in terms of what we learned with systems. So our first guess would be, well, 2 is an eigenvalue, 1, 1 is an eigenvector. So let's do C1 e to the 2t, 1, 1. But the problem is we need a second solution. Remember, usually for this 2 by 2 systems, we had a C1 and C2. So here we do need C2 times something. And well, let's think about this a little bit. Based on what we know about repeated roots for second order ODEs, a natural second guess would be x of t, again, is C1 e to the 2t11, plus C2 t e to the 2t11. Now, it turns out this is wrong, but not that wrong. So it turns out the correct solution is almost this, except we need to add some other terms here. And this is sometimes called a generalized eigenvector. So step 3. Again, generalized eigenvector. Eigenvector. Which is kind of a good substitute for an eigenvector if there's not enough available. Yeah? Think like instead of having fresh fruit, you buy frozen fruit. So instead of having an eigenvector, you have this generalized eigenvector. And I will explain in the next video why this works, but for now, let me just show you how it's done. So here's a trick. So instead of solving a minus 2iv equals 0, 0, because that would give you an eigenvector, let's solve a related equation. Solve a minus 2iw equals 1, 1. 1. So in other words, instead of figuring out which vector gives you 0, 0, figure out which vector gives you 1, 1, which again, here's the eigenvector. So this is the magic equation of today. So a minus eigenvalue I times your new unknown equals to your eigenvector. And let's do that. The good news is we already have a minus 2i. If you look at the work above, so this thing was a minus 2i. So you just repeat this. So do a minus 1, 1, and a minus 1, 1. So that was a minus 2i. But now instead of putting everything 0, put 1, 1. And try to row reduce it as usual. So this gives you, again, if you subtract the first row from the second, we have minus 1, 1, 1, and 0, 0, 0. And that would give you minus x plus y equals 1. And so y is x plus 1. And so in this case, you vector w, which is xy, that is x, and then x plus 1. But really, x is x plus 0 here. So this becomes xx plus 0, 1. And this is x times 1, 1. So in fact, your eigenvector and this new vector, which is 0, 1, and that's the thing we want. Okay. So out of this whole thing, let's extract 0, 1, which is called a generalized eigenvector. Eigenvector. And it turns out this is precisely the info that we need. So here is now the correct solution. solution. So x of t, so the beginning was still correct. It's still c1 e to the 2t times 1, 1. And now c2, still t e to the 2t times 1, 1. So that's second guess. But now you just add this new term, which is e to the 2t times 0, 1. And once again, I will explain this in the next video, why we actually do that. Yeah. And again, just two remarks. Again, the 0, 1, that's what's called a generalized eigenvector if there's not enough eigenvectors. And very important, this is a number one mistake I've seen. While it is okay to rescale eigenvectors, do not rescale generalized eigenvectors. Realize eigenvectors. Because it turns out it will change your equation completely. Eigenvector. So, for instance, if you had 0, 1, do not multiply this by 2 and get 0, 2. Or if you had 0, 1/2, don't turn this into 0, 1. All right, and now your favorite part, the face portrait. Right, so once again, let's draw the axes, nice and big. And before we do anything, let's do an orientation check once again. So let's start with the point 1, 0 and see what the solution, like how the solutions curve. So orientation check. So let's say x0, let Lexington, no. Let x0 be 1, 0. Then once again, by our ODE, x prime of 0 is ax of 0. So that becomes 1. Let me see what is the matrix. 1 minus 1, 1, 3. And then 1, 0, which becomes 1 minus 1. So what does the solution look like? At the point 1, 0, it curves down or it moves southeast. Okay. And now, what about everything else? So now let's go back to our face portrait. And maybe I'd like to remind you, so x of t was c1 e to the 2t 1, 1 plus c2 t e to the 2t 1, 1 plus e to the 2t 0, 1. So here, let's draw our two axes. So there's a eigenvector axis and the generalized eigenvector axis. So 0. And you have to understand, so the main thing here is the eigenvector axis, okay? Because the generalized one is just like a pseudo eigenvector. So we only really care what happens at 1, 1. And so let's look at 1, 1. Because of the e to the 2t terms, solutions go out. So you draw arrows here. And once again, at 0, 1, we don't really care what the solution moves like. Now, let's think a little bit in terms of long-term behavior, meaning t goes to minus infinity and t goes to infinity. as t goes to infinity, all those terms go to 0, meaning kind of the solution, they all start out at the origin. And then, so that was kind of t goes to minus infinity. Then at t equals 0, if you're on this axis 0, 1, this C1 is 0. And so what we end up getting is C2 times 0, 1. Okay, I will write that down, everything. So C2, 0, 1. So at some point, we expect the solution to go through the axis 0, 1. And finally, as t goes to infinity, the biggest term here is te to the 2t. So all the other terms, think of them negligible. And in the end, what prevails is this te to the 2t times 1, 1, which eventually becomes parallel to 1, 1. So what have we learned? The solutions, they all start at the origin, go through the axis 0, 1, and eventually become parallel to 1, 1. So sort of what it looks like is as follows. Again, you start at the origin, you curve, go through 0, 1, and then eventually become parallel to 1, 1. So whoosh like that. And maybe let me do a couple more whooshes like this. You see, they all become parallel to that yellow axis. Maybe one more whoosh. Second. More whoosh. And then what about the other side? Kind of the reverse of that. So once again, you start at the origin, you curve, you go through the axis, and eventually you become parallel to 1, 1. Whoosh. Kind of like that. And then kind of like this. Let's see, maybe that. And then finally more like this. I know it becomes a bit of a mess, but then let me show you kind of a nicer picture of what's going on. But by the way, you may wonder, why not curve the other way around? Like, why is it not something like that, where it goes like, goes as follows? Let me say like this. So why doesn't it curve this way? And that's because it wouldn't match with the orientation. You see, you have this arrow 1, -1 that goes southeast. And in fact, the solutions curve that way as well. And once again, let me show you a nicer picture of the situation. So you see, here's a nicer picture where we have the axis 1, 1, and the solutions, they start at the origin and then bend. And you can't see this well here, but they go through the axis 0, 1, and then eventually become parallel to 1, 1. So once again, to summarize, because I know this is a tough pill to swallow. So summary, first of all, again, you do the orientation check, and then as t goes to minus infinity, we have xt goes to 0, 0. That's one thing. So really, they start out at 0, 0, at 0, 0. And then the second thing is, if you're on the axis 0, 1, so if C1 is 0 and t equals 0, then x of t is C2 0e to the 2t times 1, 1 plus e to the 0, 0 times e to the 0 times 1, 1. plus e to the 0, 0, 1, which is C2 e to the 0, C2 times 0, 1. So you are on the 0, 1 axis, goes through 0, 1 axis. And then finally, as t goes to infinity, x of t then roughly becomes C2 t to the 2t times 1, 1, because t to the 2t is the biggest term. And what we end up getting, we get something parallel to 1. So those are really the three main things to see in this picture. And in the next video, I will show you why all this works, why we have generalized eigenvectors. But then if we want an extra practice example with this, check out the example in the notes that's been worked out.